Okay. All right. Welcome back. Today we're going to be doing the proof for Theorem 855. So let's first read it out, see what it's saying. So let V be a finite dimensional vector space and N be a nilpotent linear transformation on V. Then we're saying that there exist vectors V1 through Vn and some scalars, or I should say non-negative integers. So that's why the natural is M1 through Mn, such that we have A and B. A states that N applied M1 times to V1, and if you just repeat the pattern N applies to V1 and V1, and then N repeated applied M sub N times to V sub N all the way through V sub N forms a basis for V. It's a bit of a it's a bit hard to say it out, but I think just look at it, it makes more sense. And then B is a little more simple. It says that for all of the pairs M sub I and V sub I, if you apply N M sub I plus 1 times to V sub I, you get 0. So that's what we're doing. The way we're going to prove this is through induction on the dimension of V. Remember, V is always finite dimensional. So we can do that. It's going to be pretty straightforward strategy-wise. The proof gets a little hairy, but it's not going to be too bad. Let me look. Oh my God. Sorry. So let's start with the base case then. So another under the dimension of V. Then the base case, dimension of V is equal to 1. That means that the only no potent linear transformation you have is the 0 map. So then N is equal to 0. And as such, we can pick any V1, I should say any non-zero V1 in V. And we can pick M sub 1 to be 0. And then all we need to do is verify that A and B do hold. So for A, we just notice that N, which is 0, to the M1 applied to V1. This is just the 0 map to the 0, which is the identity applied to V1, which is just V1, which is obviously a basis for V, because V is just one dimension. So one vector spans everything. And now we check B. So we need to show that N to the power M sub 1 plus 1 applied to V is equal to 0. And then obviously N to the M1 plus 1 applied to V1. This is just the 0 map by 1 time to V1. Obviously it's 0. So we check both conditions and we're done with our base case. Let's now write our induction step or our induction hypothesis. And I'm just gonna take a look at my references here. So assume we're working with a vector space that has dimension greater than 1. And that for all vector spaces of lower dimension, we could say that the property holds. So let me tell you the property. Then, so this will be our induction hypothesis. Okay. Well, so the way we start out with this, the whole idea of how this proof is gonna go is that we're gonna break down our vector space V, which obviously we can't call the induction hypothesis yet, onto something that is strictly lower dimensional so that we can call the induction hypothesis on that. And once we have that basis following what we get out of the theorem, so by the induction hypothesis following all that, we'll extend it into a basis for the entire vector space V. So the first thing that might seem a little unrelated now is just noting that N is not injected. And we can just quickly go over why. So we know that n is nilpotent. So there exists some integer or some positive integer k, whatever, such that n to the power k times, or not times, applied to any vector in V is equal to 0. So we can just say that k in the positive integers be such that n to the k applied to some vector V is not equal to 0, but n to the k plus 1 applied to V is equal to 0. In other words, we're saying that I'll see if you can still see there. So in other words, what we're saying is that k is the smallest positive integer, such that when we apply n k times to this vector v, we're letting v be v. We'll let v is v. When we apply it to v, we don't get 0. So then applying just one more time, we get the 0 vector. And now to show that it's not injective, we quickly just note that n times, or not times, n applied to n to the k v is equal to 0, and so is n applied to 0, but n to the k v is not equal to 0. Therefore, the map cannot be injective. So that's the first thing we get out of there. And with this, we'll be able to show that a very neat subspace has lower dimension than V, which will allow us to call the induction hypothesis of it. Sorry. We'll leave it there. I'll see if I need to pull it down at some point. So what we have is that So what we have is that n is not injective, which implies it is not surjective. Right, because V is finite dimensional. If we have an injective linear transformation from V to itself, it obviously has to be surjective. It's one of the first things we looked on the course. And so what that means is that the image of T is a subspace, strictly subspace of V. And that tells us that the dimension of the image is strictly less than the dimension of M. And if we just recall the induction hypothesis, everything that is less than the dimension of every vector space that has dimension less than the dimension of V follows the properties, or I should say that our statement holds for it, which means we can call the induction hypothesis onto the following restriction map. So, call IH on, and that map is simple, just N restricted to the image of N. Oh, I don't know why I'm saying T here. Should be an N, I'm sorry. Did I say T anywhere else? No, it's all N's. Okay. So this restriction map from the image of N to the image of N follows the induction hypothesis. Right, so that's the map that we are applying the IH on. And so let's actually write out what we mean here. And so by IH, we have vectors v1 to vn and some positive integers, or some non-negative integers, I should say, m1 to mn, the naturals, such that, and we'll call this star. We have that. We just follow what we have from our theorem, right? That's what we do in induction proofs. So n to the m1 times v1 all the way to n v1 v1. And we just keep going. N to the m sub n, v sub n, and v sub n, and v sub n. This whole thing here, it forms a basis for the image of n. And then we also have that n to the m sub 1 plus 1 v1 is equal to all this of I, so all the way up to m sub n plus 1, v sub n, which is equal to 0. So that's what we're up to so far. And what we want to do next is somehow extend this set into a basis for V. So there's a few things that we need to do. Okay, sorry about the little cut there. There was some difficulties here, but we're back now. And so again, our goal is to find a way to shape this set here into a basis for V. That will follow all the rules that we set in our theorem. And so it might seem a little unintuitive or not so obvious why we're doing this, but we're gonna claim that another set, first of all, is linearly independent. And that would mean we were able to extend it into a basis. What that set is, the set n, let me just copy it out here. Let me make sure I don't make any mistakes. N sub n plus 1 plus 1 u1 and u1 u1, and then again it's just the same pattern here, and plus 1 u sub n and u sub n, and u sub n is linearly independent in V, where we define V sub I to be n applied to u sub I. And so what that's saying is that if we have some power of n applied to some v sub I, so that'll be just n to the k v sub I to be n to the k plus 1 u sub I. And so again, our claim is that this set here is linearly independent, and once we prove that, we'll be able to extend it into a basis. So let's do that here now on this board. And the whole idea of how this is going to work, just by the way we designed it, is we're going to apply n. We're going to first come up with some coefficients, some alphas, some a's, and we're going to show that they all have to be equal to 0 by applying n to both sides. And because our basis is just the like plus 1 ends of the u's, and then an extra u in the end, once we apply n, we'll get back, pretty much we'll just get back star. And star is linearly independent, so that'll be linearly independent too, which means our coefficients are all 0, which is exactly what we want to show. So let's actually put that on the board right now. So we want to show that this here, I'll call this maybe star star. And let's just restate what we want to show. Yep. That star star is clearly independent. So we let alpha sub I in F, and we can write down maybe alpha 1 and to the n plus 1 u1, and we keep making our linear combination. This can be maybe I should say m sub 1 here. Right, so let's put a 1 for our m, and then another one for our power. Maybe this could be that m plus 1. It doesn't really matter what we call them. I don't want to overcomplicate the naming of the coefficients, because that's not too important. So I might just write everything as alphas, just because otherwise it would be here the whole night, just putting it down, all the indexes and everything in the right place. But the point is that they don't need to be equal. They could be anything. Every single alpha right here could be something else. We'll show that they all have to be 0 anyways. But just keep in mind that this alpha and the next alphas I'm going to write are not the same. I'm just putting some generic alpha in, just so that we don't have to go through coming up with how to like index it and everything. I'll just write alpha. I guess the whole time I wasted just explaining why we're gonna do that would be enough time to actually do it. But yeah, so that's what we're gonna do. So we have n u1 plus alpha u1, and we just keep going. We have alpha n sub n plus 1 un, exactly what we'll expect. Well, this is just u1 alpha u1. We equate this to 0. And now the whole trick is to apply n to both sides. So we say n of this whole thing is equal to 0. Obviously, n of 0 is 0. We don't really have to explain why it's linear. So map 0 to 0. Put this here. Okay, there's a quick adjustment. So what happens when we actually apply this? Well, let's take a look. We got alpha times n. So what we do, basically what we do is substitute this back into our v's. So let's just do that first. N times alpha, this is just m1 b1 plus, then here we're gonna have alpha n times u1 is u1 plus here we can't do anything, so it's just u1. Now when we apply again, when we apply n to this, all we need to notice really is that this is the same thing as star in here, except for the use of except for what we have here, the alpha use of i's. But once we apply n, we'll actually get exactly star. So we'll get everything set to 0, exactly how we want it. So this would just be equal to star implies alpha is equal to 0 implies really independent. Let me just recap why this is the case. I should call this like star prime because it's not exactly the same. But we pretty much have star in here. And so for all of those elements, obviously we know that they're independent. So that would mean that well, that would mean that we have zeroless coefficients, except for maybe these terms. But then again, when we apply n to this whole thing, we go by property B of the induction hypothesis. And so that clears things out in that case too. So let us now probably, actually we might not even have to clear a board. Well, 230. Okay. I think it looks usable. So we're up to, oh, let me pull it down. All right. So we're up to star. Right, it's a bit of a, let me just make sure I'm in frame here. Okay, so about there, I'm in frame. So up to star again. Well, so what we've shown is that this set here with the use events is linearly independent. And now that we have a set that is linearly independent in V, we can extend it to a basis of V. Again, this is very early course content. So let's just extend it and see what we get. So we're gonna have m to 1 plus 1 u1 m to the m to 1 u1. Well, this is interesting. u1. Well, anyways, n to the m to the n plus 1. Use of n. I know it's bad too. Oh, you gotta fix that. But anyways, u1, and now we extend it into a basis, so we just add some elements. W1 to WP. So what we've done here is extending into basis for V. Okay, so let's get back to it. I've gone ahead and written a few things down since the last cut. And basically what we want to get again is this set into something that is a basis for V. And now one thing we gotta note is that n applied to the W sub i's we have here at the end of our list, it's obviously in the image of n, just by definition. But what is the image of n? The image of n is the span of the spaces that we get from star. And what else do we know about star? Is that star is just n applied to something. What I mean to say is every element in star is just n applied to something in star star or in double star. So what that means is that there's some x and y in star star such that n applied to x of y is equal to n applied to w sub y. So what that allows us to do is to come up with a new element, a new vector. We call it u sub n plus I. U sub n plus I. And we'll define it as the most obvious thing that comes to mind, just w sub I minus x sub I. And we're gonna basically replace our w's with that in the list. Just one thing to note then, note that obviously n applied to u sub n plus I, that's just equal to n applied to x sub I, or to w sub I, minus n applied to x sub I. And we have that they're equal, so it has to be 0. So by using these vectors, you can already tell that B in the clause B in the theorem will be satisfied. Mainly if we pick all of our m sub i's, like for this whole part of the list here, we pick our m sub i's to be 0, and we'll be able to satisfy the list. Of course, why we'll be able to satisfy the list? Well, we know that the length of the list will be the same because we're just replacing each w sub I by one u sub n plus I. So then we'll maintain the same length. And because we've already shown that it's independent, if they have the same length and one of them spans, the other one has to span. So that's how we know it has to span too. And then the last thing we need to show that like it actually spans is that, well, we know we can describe it with the w sub I. So can we describe it with the u's? Oh, of course we can, because every one of the u's has an element of w and has an x of I too. But x of I is just in star star, which is already contained in this whole list. So that finishes up the proof. Just to restate, let me see. Yeah, I'm on the board still. Okay, so I guess I'll restate here. We can by choosing or u sub n plus i's to be equal to or w sub i's minus or x sub i's. Again, x sub y are the ones we have in star star, which are right there on the top. And we'll call them m sub n plus i's to be 0. Theorem 855 is satisfied. And so that's our little square. And yeah, that's about it. So let me just quickly restate one last time this last part, just because I felt it might have come off a bit confusing, or I should say, let's just quickly recap what we have. We start out with the restriction map, just looking at how n behaves on the image of n, because we know that the image has dimension strictly less than the dimension of v, and since we're using an inductive argument, that's what we need to call the IH, right? That allows us to use the IH and get star. So we generate this basis for n. From star, we generate star star, which is basically, if we think of taking a step back, so where each of the u sub i's or each of the vi's is n applied to one of the u sub i's here, and we've shown that that is independent, right? And now because we have a linearly independent set in V, all we can do is extend it into a basis for V. So this is our new basis for V. And we can do some quick manipulation by just using u sub n plus I instead of w sub I. And the way we do it is we still use the w, but we use an x, where x is something in star star, which is basically like this whole part of our set. This is all just star star. Here. Right. Star star. So we're using an x that is somewhere in here. And since we're using the independent w, we're still describing exactly the same space. So these two sets, or I should say like finally like this set. So the set n to the m to y plus 1 times u1 n to the m1 u1 all the way through n to the m sub n un plus 1 un and un, and then we have un plus 1 all the way up to un plus p. So this is our new basis for all of v. Again, the spanning argument is just what I said. We have that this whole thing is star star. Here we have independent vectors from star star. And so we also have that these are independent vectors from star star because we're taking away kind of like the dependent part from star star by using that. So we have that it's spanning. It's the same size of this, so it must be a basis. It's also, so it must be spanning because it's the same size. There's a lot of different arguments you can make. But I think the main takeaway is we can boil it onto that, and like the way that actually works is those vectors we use to extend it, we just pick our m sub i's to be 0. And so then we can satisfy A, right? Both A and B. So this is the part that satisfies A. And then satisfying B, of course, if you raise n to the 0 plus 1, that's our plus 1s, and apply it to all these remaining vectors here, this is what we get, 0 again back. So I hope it wasn't too confusing. And yeah, let's just pull it back here one last time. That is theorem 855. All done. Hope you have a super nice break. And yeah, bye-bye.